Computer Science 461, Formal Methods Part 3, and you'll notice there's a lot of Z's down there, and that's because Z does tend to put people to sleep, so we'll try to keep this brief and crisp. This is our last Formal Methods lecture, so we'll try to finish it off. A couple requisite cartoons. This is one of my favorites of all time by Bill Watterson's Calvin and Hobbes. Calvin says, I don't think math is a science. I think it's a religion. Religion? Yeah, all those equations are like miracles. You take two numbers, and when you add them, they magically become one new number. No one can say how it happens. You either believe it or you don't. This whole book is full of things that have to be accepted on faith. It's a religion. And in public schools, no less. Call a lawyer. And as a math atheist, I should be exempt from this. So, sorry for the poor quality of the scan, but it's an oldie but goodie and it's a great one. If you wanted one of the formal methods, here's one for you. And basically, don't let this happen to you. Formal methods folks are very, very serious about their development methodologies and making sure you use consistent axioms. So, we'll talk a little bit about semantic types. And semantics are the study of meaning. There are three main branches of semantics. One is axiomatics, where we look for meaning in terms of preconditions and postconditions for a program and apply proofs to show they are correct. This kind of corresponds to Grice and Dijkstra's work in the area, and you may have seen these preconditions and postconditions in Chapter 3 of the discrete math text. Denotational, we look for meaning in the expression of functions, and so Z is part of denotational semantics. And last but not least are the operational semantics, where we describe the computation and hence the meanings in terms of a machine or a model. And basically those are example of that as abstract state machines. These are important if you want to look into different types of formal methods, but just remember that Z uses denotation. So we'll take a little overview of Z and see some of the details of it. We'll start with objects and types. So why all of this notation in math? As Calvin says, you should be exempt from this as math atheists, but basically objects from discrete math can be used to model data structures, which is one of the reasons we require it. So tuples can express records, relations can model tables, linked data structures such as linked lists, functions can do lookup tables, trees, and lists, and sequences can do lists and arrays. So the data structures that you use in 321 throughout computer science are based on objects or ideas from discrete math. And mathematics also provides precise meanings for operators. So the chapter 2 of Spivey explains which mathematical objects in the specification can appear and what their meanings are. So we'll start out with types. You've seen types such as name and date in the birthday book specification. Every expression that appears in a Z schema is associated with a unique type. So a type is an expression or a restricted kind. So it can be a given set name or a compound type built from simpler types. The value of the type is called its carrier. So any set of objects that are a member of the same type T is an object of the set type P of T. You can write sets in Z by listing their elements, enumerating all of them. For example, CS151, CS450, CS461 might be a set of classes that somebody's teaching, or giving the standard mathematical type, the set of natural numbers in the second bullet there. Or giving a characteristic property. For example, P is a person, and the age of that person is greater than 19. So these are really the three types of composite types mentioned on page 25 of the Spivey text. You'll also see free types, which are enumerations, and you'll remember those from the reports in the birthday book example. So you could enumerate, a small set of colors: red, green, blue, yellow, cyan, magenta, white, and black. And basic types, which can include infinitely many elements, such as the names, dates, processes, or files. Tuples and Cartesian products. If X is a member of the set T and Y is a member of the set U, then the ordered pair X, Y is an object in the Cartesian product type T cross U. We can extend this construct to include a tuple that is a member of a Cartesian product of n distinct sets. Now, remember that parentheses matter. For example, the tuple ABC is not equal to the tuple A, comma, the tuple BC. these are different types, so associativity and commutativity matter. However, if you have two ones where you have x1, x2 to xk, and y1, y2, yk, and each one of them is correspondingly equal, then you can say the two tuples are equal. Tuples can be used to resemble structures in languages such as C++. Bindings. If P and Q are distinct identifiers and X and Y are objects of type T and U respectively, then there's a binding Z is equal to P gets assigned to X and Q gets assigned to Y, such that Z.P is equal to X and Z.Q is equal to Y. And the binding is also a schema type. These are used in operations in Z which allow instances of a schema to be regarded as mathematical objects in their own right. They can also be used to describe the meaning of predicate parts of schemas, and if you want to view this in terms of procedural programming, then it's a bit like instantiating a variable. So far we've seen sets, tuples, and bindings. These are the three fundamental types of objects in Z. We can also have relations and functions. So a relation between objects is expressed in terms of its graph. Basically, Z views functions as different from the way that programming languages view them. More mathematically is how Z views them. In implementing a specification which talks about functions, design decisions will have to be taken about how the data structure modeled by the functions is to be represented, but the specification abstracts the detail. So relations are sets of tuples. They can resemble tables or databases. For example, binary relations are sets of pairs, name and phone. And name can map to phone. So you could map Keith Edwards to 808-932-7522. So an R-area relation is a subset of a Cartesian product of R sets. Now, when R is equal to 2, we have what's known as a binary relation. And if P is a relation from A into B, and AB is a member of P, then we say that A is related to B under P. And we can model binary relations in Z by their graph. The graph of binary relation is the set of ordered pairs for which it holds. And this is a slightly different use of graph than you've encountered most of the time. And you may recall it from discrete math, since we did use it there. A function is a special type of relation. In Z, a function is a binary relation that relates each object on the left to at most one object on the right. So, that is, we don't deal in indeterminate functions. These are sometimes useful, but we're not going to deal with them in Z. So, an example of an indeterminate function is f of x is equal to a or b. Sometimes it could be a, sometimes it could be b. But it's not determinate. In Z, we want determinate ones. Z has a notation for a variety of different functions, and we'll take a look at these on this slide. Basically, you have all kinds of different functions. And you'll remember a lot of these from your college algebra class. You may see others in more advanced math classes that you take. We used to use the terms one-to-one, onto, and into. These made a bit more sense than the current nomenclature of bijections, surjections, and injections. But you can see the formal properties down below in case you ever need them. Okay, properties and schemas. Basically, in order to understand schemas, it's necessary to understand their property. So the signature is a collection of variables, each with a type. This is kind of similar to the signature of a function in procedural programming languages such as C++. Signatures provide a vocabulary for mathematical statements or predicates. And we've seen both of these constructs in our schemas for the birthday book, but we haven't formally defined them until now. Signatures are also associated with a schema type. So a schema is a signature together with a property over the signature, as in Aleph. Here you have xy as a member of Zal and x is less than y. We call x and y the components of Aleph in this example, and it's sometimes simplest to think of the components as the variables in the signature. We can also combine properties of schema using logical operations or connectives in the schema calculus. So here we have and, or, not, implication, and logical equivalence, also meaning if or only if. And you've used this notation for a lot of computer science and math classes, so I would imagine you're pretty familiar with logical operations and connectives. We can also use quantifiers to strengthen statements made in our properties. There's the existential, which means there exists. There's the existential and uniqueness quantifier. That means there exists and it is unique. So the Z notation is slightly different from the standard, which is E backward E exclamation mark. Here you have backward E with a subscript 1. And then there's the universal quantifier, which means everything in that set possesses those properties. All three quantifiers, of course, are subject to the universe of discourse, the set under consideration. So we also have decorations. We can apply these decorations to abstract data types within our schemas, and we saw these in the birthday book. The apostrophe means the final state of an operation, or the update version will have a certain property. Exclamation mark indicates an output, and question mark indicates an input. You can also rename schemas in Z. This isn't frequently done, but if S is a schema, then SY1/X1YN/X1 basically replaces each X sub I with the corresponding Y sub I. Signature in new schema is obtained by the signature of S by replacing the renamed components and merging any duplicate components. And again, in practice, you don't see that very frequently. You can also combine schemas. Two signatures are said to be type compatible if each variable in common to the two has the same type. So here we can see B is in common between those two. It's X cross Y. And they're the same, they're type compatible because B has the same type. And then we can merge them to make the signature with A, B, and C. Now, if B was part of X cross Y cross Z in the second term, then we might have to rename B in the second schema in order to merge them. But we can still merge them. We just have to use a different variable name in the second one. We can also combine two schemas with type compatibility using the conjunction operator. So here we have Aleph, which is X and Y are members of Zol. X is less than Y. Y is a member of Zol. And Z runs between 1 and 10. And the property there is Y is equal to Z squared. So combining these with and, both X and Y are members of Zol. Z runs between 1 and 10. X is less than Y, and Y is equal to Z times Z. We can also combine schemas using the other logical connectors, and we can expand them textually, but we also have to be careful. And by careful, I mean to say you need to remember things such as De Morgan's laws when negating connectives and quantifiers, as seen in this example. When you negate the conjunction, you get the disjunction and the negation on both sides. We can also use quantifiers in a schema. For example, consider the case where we want Z to be greater than 5 in Gimel. Gimel with Z greater than 5 is Y is a member of Zol. For all Z is a member of Zol, Z is greater than 5, such that Z is also 1 to 10, and Y is equal to Z times Z. This one can actually be further simplified. In fact, you can eliminate the thing after the black dot. Variables and scope. So when employing nested scopes and local variables, it's best to have unique names for the inner variables. And this is good programming practice in general. In regard to local variables, you don't want local variables to, especially for a loop or a block in C++, to have the same name as something outside of that block, because you get very confused very quickly. So I've seen students put local variables inside of blocks that have the name of a variable outside of the block, and it can be really nasty, particularly in languages like JavaScript that really allow you to abuse that. Schemas with global variables, and again, Spivey refers to them as global variables, but they're really restrictions on variables used in the program or global constants. So we often need to have global variables, for example, file path or an upper limit on arrays, and again, these are more constants. We can declare global variables in Z by using the following notation. Basically, here you have what looks like a partial schema. Here, limit is a member of the natural numbers, and limit is less than 65,535. We don't have to declare this variable locally in any schemas in which we use it, and the usual programming warnings concerning global variables apply, particularly if you're changing that. If you're using it as constant, everything's cool. Generic constructions. It's also possible to have generic schemas, such as one that describes the allocation of resources. So here you have a pool of resources, and the resources map to individual users. You also have a set of free resources, which is a set of resources. And the domain of owner union with the ones that are still free are the set of resources available. And you can't have one that has both an owner and is free. And so basically we can pass the parameter of resource. So we describe the state space of resource manager program, for example, disk pools. And the constraints and signature of the schema are pretty obvious. Generic constants are generally more useful than generic schemas. These capture concepts such as relations, functions, and sequences. For example, you can define the domain and the range of a relation as given in the following schema. And you can put that in your Z specification generically. In mathematics, we often have functions that are not defined at all values. For example, division is not defined for 0, unless you're Chuck Norris. The tangent of x is not defined for pi over 2, and the natural logarithm of x is not defined at 0. So in general, we have to have well-defined functions by either defining their value at every possible point or by restricting their domain appropriately. So you can say division only works for positive and negative, but not for 0. So you can restrict its domain. So that covers chapter 2. If you're curious about the rest of the text, you can take a look at it. It is posted under the resources in La Lima. And because I'm keeping this fairly short, we're not going to explore the rest of the text in detail. But high-level overview of it, Chapter 3 is going to talk about the Z language itself and gives detailed explanations of expressions, predicates, generic constants, generic schemas, and free types. It also gives a grammar. Chapter 4 gives detailed background on set theory. Chapter 5 discusses the use of Z specifications for sequential programming and describes their state spaces. And Chapter 6 gives a complete and concise syntax for Z. There's also a glossary and a useful table of symbols starting on page 153. I know that you're sad that we're not going to have more lectures on these, but if you do feel really bad about it, you can read the text. So next time we'll get into verification and validation, which I believe is Chapter 8 of the Somerville text, and I'm also going to bring in some material from Pressman about testing that's a bit more detailed than Somerville gets into.